problem based on equivalent fundamental statements. So here we are going to perform few problems which are based upon the equivalent fundamental statements of part 1 under the advanced level. Then now, so here under the part 1, in the problem which we are going to consider, say here we need the two statements, one as P, the other as Q. Then now here the illustration or the nothing but the problem number 1 is of prove that the condition is of negation of P implies Q is identically equals to P and negation Q. So here in this case, so negation of P implies Q. So here when we remove the implies symbol, then the negation will be attached only to the second statement, that is the Q. So here then the implies becomes here the AND. So this is one of the formula which we use under the law of algebra of statements. So this will come under one of the law of algebra of statements. The negation of P implies Q is identically equals to P and negation Q. Then now in order to prove this condition, so the proof starts now. So in our proof, so as per the problem or as per the condition which is given to us, so as per condition or the statement which is given to us is of negation of P implies Q is identically equals to P and negation Q. So here this is to be proved condition. So here in order to prove this condition, we have to suppose two statements, that is one as P then the other as Q. So here let P comma Q be two statements. In order to prove this condition, so here we have to write the truth values of the left side, that is the left side simple statement, and as well as the truth values of the right side simple statements. In case if we are able to show the truth values of the LHS and the RHS statements as similar or the same, then we can write the negation of the P implies Q is identically equals to, or in other words the equivalent to P and negation Q. So here by showing the given condition or the given statement, by means of the truth values in a truth table. Then now the next logical step will be of, say here, so this is the truth table in which the condition to be proved is of the negation of P implies Q is identically equals to P and negation Q. So this is to be proved. Then now the truth table for this condition is of, whereas in this truth table we have to assume the two statements, one as P and the other as Q. So under the column number 1 and column number 2, so I am going to assume the two statements, one as P and the other as Q, and the remaining columns are of 3, 4, 5 and 6. Then now, whereas in order to prove this condition, so here on the LHS we need negation of P implies Q, and on the RHS we need P and negation Q. So here the bracket indicates say here negation Q, whereas in the next third column I am going to take a say here negation of Q, the latter. So LHS needs, so LHS is having the P implies Q within the small brackets. So first of all let us find out the implication of the conditional of a conditional statement of two statements, that is P and as well as Q, so that is P implies Q. Whereas in the next column let us find out the LHS overall, that is negation of P implies Q. Then now under the sixth column let us find out the right side statement, that is P and negation Q. So here when we assume a statement that is a single statement, then the truth values will be of true. Say either the statement may be of true or the false. So there are of two truth values, but not both. Whereas here we assume two statements, so the possibilities will be of 4. So both the statements may be of true, or both the statements may be of false. And if one is of true, the other will be of false. If the first one is of false, the second one will be of true. So in this manner, let us take the truth values of these two statements. So both as truths and both as falses. If the first statement P is of true and the truth value of the second statement will be of false. If the first statement P is of false, then the truth value of the second statement Q may be of true. So here these are the 4 possibilities of the truth values of the two statements, that is P and as well as Q. Then now under the third column, that is we have to find out the negation of Q. So here Q is of true, the truth value of the Q under the first row is of true, then the negation of Q, that is not P, so not Q, so it is of not true. So if it is of not true, then automatically it must be of false. Whereas here the truth value, in the next case we are taking it as the false of the statement Q, then the negation of Q, that is not Q. So in case, so the truth value of Q is of false, then not false indicates the true. So here Q is of true, then the not Q is of false. Then if the Q is of false, then the negation will be of true. Then now, so here in the next column you have to find out the P implies Q. So here is the implication. In case of the implication or the conditional statement, so the condition is of, if the statement P is of true, but a conditional statement, in case of a conditional statement, a true statement does not implies the false statement, that is the second condition, that is the second statement Q is of F, then the condition also will be of F. So this indicates that a true statement does not implies the false statement. So first statement must be of true and the second statement must be of false, therefore the implication or the conditional will be of false. So here to find out the conditional, that is P implies Q, we have to search P and Q statements. So P and Q statements are under column number 1 and column number 2. So first statement must be of true and the second statement must be of false. So we have to search T and F. So here under 1 and 2 columns, T and F is not there, whereas here T and F, P is of true and Q is of false, therefore the conditional statement also will be of false. Whereas here in reverse case, F and T is not possible, both are F. So here the remaining all will be of true. Then now negation of P implies Q, whereas this bracket indicates the conditional P implies Q is under the column number 4, but we have to find out its negation. So here P implies Q is true and its negation will be of false. So here P implies Q is of false and negation will be of true. So true and the negation will be of false. So here P implies Q is of true, then the negation will be of false. Then the latter. So we have to find out P and negation Q. So here this connective and indicates the conjunction. So in case of a conjunction, we are going to find out the conjunction of the two statements. One is of P, the other is of negation Q. So here condition of the conjunction is of. If the first statement is of true and the second statement negation Q is of true, then the conjunction also will be of true. So this is the condition of a conjunction. So here under P and as well as under negation Q. So here these two are of. P is of column number 1 and negation Q is of column number 3. So we have to search column number 1 and 3. So here both must be of truths. So the truth values of P and as well as negation Q must be of true. There only the conjunction will be of true. So here under 1 and 3, so we have to search for T and T. So T is not there, whereas here second row is having T and T, that is the truth value of P is of true and the truth value of negation Q is also true, therefore the conjunction also will be of true. Then the next one F and F, so here F and T is not possible, so here the remaining all will be of falses. Then now, so here in order to prove this condition, so here negation of P implies Q, negation of P implies Q is under the column number 5 So here P and negation Q, P and negation Q is under the column number 6. So here let us see the truth values of the columns, that is 5 and as well as 6. FT FF. So here also FT FF. So here the truth values of the columns 5 and as well as 6 are similar. Therefore, negation of P implies Q will be identically equals to, or in other words equivalent to P and negation Q. Then now in the next logical step, since the truth values of columns 5 and as well as 6 are similar, so here hence negation of P implies Q is identically equals to P and negation Q. So here hence it is proved.